Hi there, and welcome to this video tutorial about the Leadwerks engine and Astar pathfinding with C#. Now this is going to be quite an interesting tutorial because we're going to do a lot of coding. I'm going to explain a lot about the Astar algorithm, and we're going to have an awesome demo or showcase all working and ready and well playable, and that's something you should be able to use in your own project. Okay, I made a little PowerPoint presentation which is going to help me along in this entire tutorial because it's going to be quite a long tutorial. And I'm just going to start that PowerPoint. Aha, there it is. So this is what we're going to talk about. First off, I'm going to do a little introduction. That's what I'm doing right now. Then I'm going to explain the Dijkstra algorithm. What is the Dijkstra algorithm and what has it got to do with the Astar algorithm? Then what is pathfinding in general? Then we're going to set up the project. I'm going to start talking about how to create tiles and how to make a grid, etc. Then we're actually going to talk about the Astar algorithm, what the pseudocode is, and how we're going to work on from there. And once the entire code is working, we actually need to get the path. And how we're going to do that, well, we'll see it when we get there. And afterwards I will talk about some improvements, because I'm not gonna explain everything in this tutorial. About, for instance, different heights or different models, from model to height, for instance. That's not something I'm going to cover in this tutorial. It's purely about the Astar algorithm itself. Okay, now let's start off by explaining what the Dijkstra algorithm is. Dijkstra is a Dutch, or better said was, a Dutch scientist. He died a couple of years ago, unfortunately, and he invented an algorithm, an uninformed searching algorithm, to get from one point to another in a very short way. So here we have point A, and we need to get to point F. So what is it what Dijkstra does? He's going to look, now, what are all the adjacent nodes, but in this case B and D. And from those points on out, I'm going to check what are their adjacent nodes and what is the shortest path from there. D has a path length of 10, while C has a path length of 5 and 1. That means that we can discard B for the second, and now C and D are in our so-called open list. These are the leaves of our entire structure. And then we're going to check a little bit further. What's closer, F or E? Now, of course, F is already our goal, but is it the fastest path? Because now we have a path of 17. So we're going to look 5 plus 1 and C to D. Now, we don't need that, but is it shorter from A to D or from A, B, C, D? And in our case, that actually is the case, because 5 plus 1 plus 2 is 8. So that means that when we would go to E, that although we have 5, 1, and then 8, that this is a lot faster than just going from A, D, E. Now we repeat all those steps like this, and then we can finally see that we have a shortest path available, which is A, B, C, E, F. Now, of course, this is a really fast way of explaining Dijkstra, and it isn't really important at the moment if you understand it entirely, but what is important is that you know the basic guidelines from, okay, that's what we're going to do in this tutorial. So we're going to continue talking about, well, pathfinding in general. Let's say that this is your game. You have a nice terrain, and you want to get from this tower here in the top, in the bottom left, to the top right. Now, how do you do that? How are you going to get to that other side? We need to define some sort of search area. Now, one way of doing that is by creating a grid, and that's what we're going to be using in this video tutorial. Now, a lot of games use grids for their pathfinding, especially with larger terrains and stuff, but also in houses or in models that represent houses and etc. There are different ways, for instance with waypoints or with navigational mesh, but to the bottom line, the grid is still one of the most used, well, search areas, at least as far as I know. Perhaps I'm wrong. So what are we going to do with that grid? We are going to make a representation of our world, and that means that we're going to use, well, in this case, vectors, a 2D vector, to store information about what the search area is at the moment. And we could say that we start at 4.0 and we want to go to 0.6. Okay, here again only with no back image. And then I'm going to show you real quickly what we're going to do with Astar. So here we have this starting node, and we want to get to B, the yellow one. And these stars here, they're non-walkable, so we have to get around it. And what we're going to do, we're going to check which paths are available next to it, the adjacent tiles. And then we're going to calculate the cost to get there. Now, in this example, you can go horizontally and vertically and also diagonally. But we're not going to do that in our tutorial with our demo, because it's going to make it a little bit more difficult. Not that much, but we're just going to keep it as simple as possible. Okay, let's start up the project that I've already set up. You can easily make this kind of project by using the LE builder that comes with the Leadwerks SDK. So I'm just gonna fire this bad boy up. Yes, there we are. And all I have is the main class, which is actually the Astar. Oh, I have called it Astar. Huh. Well, pity. I call it Astar test. Cool typo. And all I'm doing here is actually creating a camera, I'm creating a light, and a large plane, which is going to be like the background where our world is being displayed on. And the only thing I do here is some really simple camera movement with some mouse rotation and moving forward with WASD. And I'll just run this real quickly. And you can't see much because there's actually nothing there. There's just this boring grey plane and the sky's all black. Okay, so that's it for this first part. Let me just pause this for a second and we can continue. Okay, now let's get actually started with making our little Astar pathfinding showcase. We are going to make a grid. And the best way to make a grid is by storing our tiles in an array. But let us first declare a couple of variables. For instance, I'm going to make a public static integer, because I want to address these variables later in different classes. I'm going to say grid width, and for now I'm just going to say 10, and I'm also going to make a grid height. In case you didn't know, you can make this variables of the same data type in a single row. Okay, so every time we want to address the grid width and grid height, we can just use Astar test dot grid width. That really comes in handy later on. And what we want to do now is we want to make a nice grid. And a really nice way of doing that is by, as I said before, making some sort of array, and in this case making our grid, and in this case it's going to be a multi-dimensional grid. And I'm going to make that out of objects called tile. Now, tile objects do not exist. We're going to make them in a couple of minutes. Now I'm going to say tile, and by doing this I'm going to make a multi-dimensional array. This differs a little bit from Java, so watch that. We're in C# here. I'm just going to call this grid. I'm going to say new tile. Awesome. New tile, and then the size is the Astar test dot grid width, and of course the Astar test dot height. Okay. Not gonna give you an error, but that doesn't matter. We're gonna fill up this grid with new tiles, and to do this we're gonna make a for loop. If you type in 4 and you're inside Visual Studio and you double tap, then you automatically complete this for loop, which is just really convenient. But of course you don't have to do this if you don't want to. I'm going to say the grid width, times actually, because when we're inside this for loop we want to start another for loop. You know, it's like for loopception or something like that. And this can be really useful because now we can fill up the entire grid and just using these two for loops. Astar test, and this time grid. Whoop, grid height. Yes. Okay. So in this new grid we want to make a new tile. So we're gonna say grid I and G as its indexes or indices, and we're gonna say, well, new tile. Okay. Make a new tile. Okay. Now let's do something about this object class, or because tile isn't anything at this moment. So I'm just going to say add a new class, and obviously we're going to call this tile. Awesome. Here it is. The first thing we want to do is make this public. I always forget that a lot, so do that. Okay, so what's inside this tile class? Well, the first and the most important thing is we want to store some sort of ID with this this tile, because we can have its position and its scale, but we need its actual ID. You know, what's its place inside this grid. And we're going to use a vector2 for this, and I need to type using Leadwerks engine, otherwise the vector2 class won't be recognized here. I'm not gonna bother about making things public or private this time. You can do that in your own time. We're just gonna make it as simple as possible. I'm gonna call this vector2 and I'm gonna call it ID. I'm going to make something that is called the T-mesh, and that is an actual part of Leadwerks. And what we want to do is we're going to make, per tile, we're going to make a cube inside of it, and then we're going to display those cubes or position those cubes at its according position, like the grid says it to. Okay. The Astar Pathfinding algorithm works with 3 variables to calculate things and to compare things. One of them is called cost, the second one is called heuristic, and a total variable. Now I'm going to use integers. Of course, you can use floats if you want to, but we're just going to keep it at integers so we can avoid difficult readings later on when debugging. Now you're probably wondering, what is heuristic? I'm going to cover that later. For now, I'm just going to put these variables here, and total, which is also 0 at the start. And then we want to say, for every tile, is it walkable, yes or no? So we're just going to add a nice little variable with a very clear name, walkable, yes. Okay, let's make a constructor. If you do not know what a constructor is, if you're making a class, for instance like tile, and when you make a new object of that class, the first thing you do is call its constructor. And the constructor is sort of like a method, but it is always called when you create a new object. So we're just going to say tile. Perfect. Public tile. So what do we want to pass along with this tile? First off, we want to pass along its ID. Yes, that's right. You know, it's always nice to affect its scale. We want to scale the cube a little bit down. Of course, its position. Tfec3 position. Now I want to pass along the cube. Why do I do that? I'm gonna make a cube inside our main class, and then instead of making a new cube inside our tile, I'm just going to copy the one from Astar test. This is going to save a lot of time and whilst creating it, and it's just better for our program. You'll see in a second why that is. And the only thing I want to do now is say, is it walkable? This ID, for those of you who don't know the difference between this ID and ID, this dot is referring to our class, which means that we're gonna say tile.id actually here, and ID is this ID is referring to the one in the constructor, the parameter in the constructor. It's really important, and it's actually really useful. You might say, well, that's kind of rubbish, but it's not. It really isn't. We're gonna say team. What do I want to do? Oh yeah, cube. This cube is, and then we're gonna say le. Oh, this works so awesome. We're just gonna say le dot, and then we want to say copy entity, and the nice documentation here says what we want to copy, and we want to copy the cube that we got from our constructor. Okay, cube. Brilliant. Am I forgetting something? Nope, not yet. Okay. I want to set it walkable. This walkable is walkable. Great. Let's just save that. And then I want to go set the position and its scale. Okay. We're gonna say mesh. Oh, sorry, cube. Oh, got it wrong again. le dot scale entity. And I'm gonna say cube, and we're gonna scale it with a new vector 3, and then scale. Oh, I could just put down scale, of course. I do not have to make a new variable here. Okay, and then we want to position this new cube. I'm gonna copy this line. We're gonna paste it, and we're gonna rename it to position entity, and of course, simply just use the position variable. Okay. So one other thing that we want to do is we want to color. We want to give our cubes a nice color so that we can easily recognize what kind of cubes they are. Are they walkable? Are they part of a path? Or stuff like that. So for now I'm just going to make a public static. Come on. What is that? Oh, that's it. Vector 4. And let's say where did I save that? Of course I need to give it a name. Let's call this one red is new tvec4. What are we gonna? Come on. And red is 255, of course. New. Okay. Now we made red, and let's say that red is every time our starting and ending position. Then we want to have green for checked tiles, black for this is black, red, green, 5. Okay, black for non-walkable. There's something else. Yeah, just unchecked. Let's just call that one pink or white. Static tvec. I know a nice value. It's cool. Let's just call it pink. It's new tvec4. 60, 60, 60. I know that that's a nice color for our tile. Okay, we're almost done. Now, the only thing we have to check here, we're gonna set a different color when the tile is not walkable. Tile is non-walkable. We're gonna say if not walkable. If it's not the case, then we're gonna say le.entity color this cube here, and we're gonna say tile dot black, because when it's black it's not walkable. Okay. Am I forgetting something? Oh yes, of course. If it is walkable, we're going to want to give it another color, and we're going to give it that pinkish color. And in a second you'll see how nice this grid is already going to look. Just going to give it a pink color. Okay. Now let's start debugging this. Oh yeah, we're not finished yet. Inside our Astar test CS, we actually have to give some extra values in our new created tiles. I'm gonna say new tvec2. I'm gonna pass along I and j as its ID, which is awesome because now we have the first tile is going to be created at 0, 0, and that is awesome. Then we're gonna have to pass along a scale, and I like my objects to be the same scale in every direction, so we're just gonna say tvec3 and I don't know, something like this should do the trick. I think that's a nice size. I think I used it in a previous project. And I'm gonna say new tvec3 for the what is it called again? The position tvec3. And what do we want to do here? Of course, we do not need to adjust the Y position because then we would be placing our cubes inside the air. We don't want that. So first off, the X axis. I don't know. Let's just say 1.3. I believe I used once before. Anyway, we can adjust that always a little bit later on. Notice how I have to use the F behind it because I'm using a float value. I'm gonna have to pass along the mesh of the cube. I haven't made that yet, so that's what I'm gonna do here. T-mesh cube, space cube is le.createCube. There it is. Fantastic. I can pass along in this function. Awesome. And then I'm just gonna say, okay, you know what? We can walk on all the tiles. We're gonna add some random non-walkable in just a second. And I see a little error here. In this second for loop, I need to change the I to a j. Okay. Otherwise, we will not have any sort of value assigned to j. Okay, let's have a test. Let's see if we forgot something. Okay, that's not entirely correct. Let's just figure out what that is. Okay, awkward. Of course, j. Blah blah blah. Oh, that's better. That's a lot better. We have now 10 of these nice cubes here standing all next to each other. Don't know if that color is correct, but that's something of later concerns. And I also see that our base cube is still there. If you can see it, it has a different height. But that's something you can remove yourself. You know what? We're just gonna do that ourselves right now. I mean, we're making a tutorial. Might as well do it good, right? So I'm just gonna say, you know what? le.hide entity, and that's gonna hide our base cube, which means that all the other cubes are hidden by default as well. So I should say this le.show entity. Here, that's one. Okay, so now we have this grid set up. I noticed we have missed a little bit. We missed the this dot here because well, I ran the program. I saw it, but I didn't tell you about it because I thought it looked quite stupid. Yes, that's better. We were missing this extra tile in the corner here. Okay. Okay, let's continue. I'm gonna go back to the PowerPoint presentation for a second to see where we are. We have covered the intro, the Dijkstra algorithm, pathfinding in general, and we've set up the project, and we've created the tiles and grid. For most part we have, because we haven't added some sort of random data to it, so that some parts of the grid are non-walkable. We're going to cover that right now, and that's actually quite easy to do. So here we have our grid, and we're going to make a random object, which is something that's by default inside C#. We're just going to say rand new random. And the nice thing about this is that we can give it a seed value, and that can be anything. And every time we start our project using this seed, we always get the same map. So in case we do not like this map, we can use a different value and see what happens. And if we would shut down our computer and start the program again, we still have the same map data. Okay, so we have a new rand value. And what I'm going to do inside the grid creation, I'm going to say rand.next, and I'm going to pass along a minimum and maximum value, which is in our case the Astar test grid height and grid width. Width and height. Do I say that correctly? No, of course not. I made a mistake there. I'm going to say 0 and 100. Okay. And I'm going to put this inside an if statement. So I can say if random.next, if that value is smaller, well, let's say 10, then I want you to make a new tile, but this tile is non-walkable. So we're going to set this one to false, and only if it's higher than 10, so pretty much else, then we're going to set it to true. Let's see, we're going to add a little comment here. Make a new tile to walk or not to walk. Okay, let's see what this does. Okay, that's pretty nice. I think we can use a little bit more. So I'm just gonna say 15. 1 or 2 tiles is enough. Yeah, that's pretty good. Okay, and this is pretty awesome because this shows how our grid generator works, and of course we can apply an enormously large grid for this. We could also say 100 by 100. You know what? We're just gonna do that because it looks really cool. Just gonna make it 100 by 100. Unless the performance really sucks, then we're not just gonna do that. Oh no, it's perfect. It's perfect. Look at that, how beautiful. We're actually outside our camera range here, but partially, because we cannot see the entire grid. But that doesn't really matter. And if we want to see some real cool pathfinding, then we're just gonna increase this value a little bit, and we have more black tiles so that larger parts are not walkable. Of course, we do have to watch out that the path that is available, we do have to look out whether there is an actual path available, because if it's not, well, then we're gonna have a problem. Okay, we have this really awesome grid. Nice. Okay, so far for the grid. Now let's continue with setting up the Astar algorithm. And we're going to use a little pseudocode here, but first off we're going to add the class for Astar. And I'm going to call this class Pathfinder. Pathfinder. Okay, great. Once again, we're gonna make this class public. We really want to do that. Okay. And what's inside this? Well, inside this class, first off, we need to have a little bit. We need to have a copy of our grid because every time we make a new Pathfinder object, we want to pass along the same grid we've been making, but we do not want to generate meshes over and over again and then assigning soldiers a different grid. We want to use the same grid, but we do need to access grid points so that we can use different soldiers on the same path or same grid. Okay, so the first thing that we're going to need is public tile, and it's going to be multi-dimensional again. I'm going to say grid, new tile, awesome, this one here, and then pretty much copy the grid width and grid height into it. We need to know what our start position is, so I'm going to say tvec2 start tile. So we need to import using Leadwerks engine. Okay, and we also need an end tile and a current tile. The end tile obviously states what the end tile is. The current tile is the tile we're at the moment searching from. So when we're inside our algorithm, we're searching from different kind of tiles, and the current tile is the one we're actually looking from. Then two important lists that we're going to keep track of is one of them is called the closed list and one of them is called the open list. So I'm just going to copy this line here just in case you're wondering where I'm getting this text from. I have a different project in my other monitor screen opened, and sometimes I will copy some code from there because it will save time. I'm going to say, now if you do not know what a list is, I'm just assuming that you are, but maybe you've never used it before. Lists are something quite similar to arrays because lists are built on arrays, and the advantage of using a list in comparison with a normal array is that you do not have to specify a size when you initiate or initialize an array. When you make a list, you say list, and then between the equal signs or the larger than, smaller than signs, you say the data type. We give it a name and we say new, and then C# automatically lists what we need to do. That's awesome. And the same thing, we do the same thing for the open list. Awesome. Okay, these are all the basic variables that we need. Now I'm going to do something else. I'm going to copy a part of the code, the commented code, from the lessons I took at game development class, and I would like to use this moment to thank my teacher Stefan Leinen and also Slobodanka Zilbrić for using this code and using parts of their PowerPoint presentation, because that's not entirely mine. As a matter of fact, most of it is theirs. So, a thank you. Here we have the pseudocode of Astar. Ooh. It looks pretty small, and if you would follow this along, you would get really far, but it's of course nicer when I just show you how this entire pseudocode works. In case you didn't know, this region and end region is really useful for just closing a part of code. Okay, let's start by making a constructor. Every time we make a new Pathfinder object, we're gonna say public Pathfinder. We want to give it along a start tile and of course an end tile. we want to give it along a cube, just in case. Do we want to give it along a cube? No, I'm just gonna, no, we do not have to give it a cube. What we do want to pass along is the grid that we're using. And like I said before, the only reason we do this is so that we can use the same grid in our entire project. So if we have different soldiers, we do not need to create an entire new grid. That would be a little bit of a waste of space. So we have our grid, and we say this dot grid is the grid we pass along in our parameter, and the same thing, we do the same thing for the start tile and end tile. Okay. Now we're going to make the actual function, that is the Astar algorithm. I'm just gonna make that beneath the guidelines, the pseudocode. We're gonna say public void, and let's just call it search path. Yeah, that's a nice name. We want to specify a starting position, start tile, and tvec2. We actually done that already here above. So I'm just gonna remove that here. Just gonna paste that back in here. Sorry for the confusion. So the only thing left the constructor does is create a new path and pass along the grid. And then when we're inside the actual search path, we set the new starting and end tiles. Okay, so what's the first thing that we're going to do inside this search path algorithm? Well, what we really want to do is we want to check whether the coordinates that we're passing along, whether they are inside our grid. For instance, we have a 100 by 100 grid now, but if you give up the coordinates -10 and 5, then you're gonna get an error, or it's not gonna work at all. Okay, now we're gonna add a region, and we're gonna call this path validation. And what are we gonna do here? We're gonna check these start tiles and end tiles, and we're gonna see, are these walkables, yes or no, or are these inside our grid ranges? And if not, then, or if they are not inside our grid ranges, for instance, then we do not want to start our path checking, because that would be pointless, and we can exit our program, or we could give information back to the gamer, or our player could simply not be walking at all. Something that we should be taking in mind. So we use a can search variable, and of course this has to be a boolean, and we want to use Pascal casing, of course, because that looks a lot better. And we're going to say we always want to search, and only if it's a not walkable tile, for instance, then we want to skip it. So we are going to say that by saying if grid and then start tile x and start tile dot y. If walkable is false, for instance, we give in coordinate starting position 0, 0, and that is false, we're not allowed to walk there, then we're going to say, well, you cannot search. Can search is false. And just to give the gamer, or ourselves in this case, some extra information, we're going to say console write line, the start tile is non-walkable, choose a different value then, and then just put in the start tile to string, just as a little bit of information to ourselves, so that we know, oh, we cannot use this start tile. We copy these lines, and we're going to do the exact same thing for end tile. I'm just going to say end tile, end tile, end tile, and also the text information is different now. Okay. Let's continue with the pseudocode, the first line of the Astar algorithm. Add the starting node to the open list. Okay, let's do that. So, start the Astar algorithm. So, if can search is true, then we're going to say open list dot add. Then we're going to add the start tile. Now that's already the first line of our pseudocode, and that is amazing because we are already done with the first step. Then we're also going to give a initializing value to the current tile. Oh, wait, let's first add some comments here. Add the starting tile to the open list, and we want to give a default value to our current tile. Okay, let's just give it a default value, current tile, and let's set it to -1, -1, just so that we have the current tile initialized. Okay, now we're going to open a while loop, and we're going to say while the open list is not empty, we'll do the searching. While open list, we can simply do that by saying dot count is not well, 0 or empty. Do the algorithm. We now want to get the current tile, and we want to get the tile with the lowest total cost from the entire open tile list. That's at this point. So the current node or current tile is the tile from the open list with the lowest cost, and we're going to make a function here, or a method. I'm going to say get tile with lowest cost. I'm going to say total. Total is better. And then I'm going to have to say what the open list is, and then I'm going to return the vector 2. I'm going to return a vector 2 that is, well, that has been calculated with the lowest cost. So I'm going to make a function here. Sorry, a method. Should use the correct words for it. Public. I'm going to return a vector 2. Vector 2, nice. And I have to pass along a list. So that's what I'm going to do here. Vector 2. I'm going to call that open list. Great. And we always want to keep our code a little bit clean. Get the tile with the lowest total value. And remember, in our tile we were calculating the cost, the heuristic, and the total, and what the cost and heuristic are. I'm gonna go over that in just a second. I want to have this set up first, and then I'm gonna explain what it does. So we use some temporary values. First off, I want to have a tile with lowest cost, and I want to initialize that with new tvec, and I'm just gonna say -1 -1 because in the beginning there isn't really a tile with a lowest total. And I'm gonna say, yeah, let's make it a float or integer. Integer is better because so far we've been using integers to keep cost. I'm gonna say, let's just call this lowest total is integer. It's integer dot max value, because in the start, why do we do that? In the start, we want to start comparing which node has the lowest total cost, and that's our current node. And in the beginning, we want to assign a max value to this. We use a for each loop to search all the open tiles. And every open tile, I'm going to say the open tile in open list. Okay. Just going to type here what I'm going to do. I'm going to search all the open tiles, and I'm going to get the tile with the lowest cost, lowest total cost. I might be using these words in conjunction with each other the entire time, but it's really important that I actually say either cost, heuristic, or total. So I'm just gonna try that from now on. Okay, I'm gonna say if the grid, yes, if grid, and I'm gonna say open tile, the one we're actually in this current loop are, open tile dot x and open tile dot y. If its total is lower or equal to the lowest total that we found so far, come on, total, then we want to replace the well, let's say the newest tile with the lowest total. I want to say lowest total is this entire line here, is grid dot total. I want to close that off, of course. But again, I have to make sure that x and y are capital. And why do I get these errors? Oh, I need to typecast them, which means that by default the tvec, or the vector2, is a float, and when I pass, I want to get the value at an index from the grid variable, and I need to convert that float variable to an integer, and that is called typecasting. We can also do, for instance, let's see if that works. No, that doesn't work here. Sometimes you also can do to integer or convert to integer. Convert to integer. That's the one I was looking for. That's also possible, but that is a little bit more typing than just doing this. So if you want to convert to a different value, different data type, then use the parentheses and the data type in front of it. Of course, it has to be possible to convert. I cannot convert a float to a boolean, for instance. Okay. As you can see, we've done already a lot of typing here, but we're nice on our way. Again, the capital Y, and again the typecasting. We're going to do that a lot. Okay, continuing with the code. So we set the lowest total so far with the newest open tile total. And then if that's actually the case, then we can tile with the lowest total is that actually the new open tile we just had. We're just searching in is this one. Does he pick that? No, we have to say new vector2. New vector2. Grid x. No, we do not have to say grid here. We just have to say that it is. Okay. So the newest tile with its lowest total is the open tile we're currently in, which has a lower total than the previous tile. Okay, and the only thing left to do here is return the tile with lowest total. So now that we've created this code, I realize that this might have been a little bit difficult to follow, and that is why I'm going to explain the steps we've been taking so far again, only this time with an image. We've already seen this image inside the PowerPoint. Let me just get to that point real quick. Okay. Here at this image here you can see 3 values at each different tile. So when we're moving to another tile, for instance horizontally, we have a so-called stepping cost. Now in this image we're using a stepping cost of 10. Now we're going to use a stepping cost of 1, just to keep things a little bit simpler. Then we're going to do something which is called a heuristic calculation. In our project we're going to use the Manhattan heuristic. I'm going to explain later on what the Manhattan distance is. Anyway, once the heuristic and the step cost are being calculated, we add these together and we can see what the total amount is. So when we compare the adjacent tiles, when we want to get the tile with the lowest cost, total cost, then we're going to look which one has the lowest cost so far. So we start off with a max value, let's say that is 1000, and then every open tile that has a lower total cost, and we're just going to set that as the new current tile, and that's what we're doing right here. Set, I can also just copy this line here. That one. Okay, perfect. Okay, let's continue with our algorithm. We've already done a couple of steps, and the next couple of steps are going to be a little bit quicker. We're going to compare whether the current tile, which we are currently at, is perhaps also the end tile, because if that's the case, then we no longer have to continue searching. If the current tile is the end tile, then we can stop searching. Beautiful. So we're going to say if the current tile dot x is the end tile dot x, and of course I can do this shorter, just comparing the two vectors, but I always like to use the end operators here. The current tile y has to be equal to the end tile dot y. Okay, so if these values are the same, then that means that we're at the end of our path, which is awesome, because that's actually what we want to achieve here. And I forgot one is sign here. Okay. And did I forget something else? Nope, I didn't. Okay, great. So now we've completed our path, and now we're moving up to else. First off, I want to say, I can actually break the entire loop, because the while loop, that is, because we're done searching and we no longer have to check whether the open list is full or empty, because we have found our object. We also want to say console write line. We are really happy that we found it, so yeah, we found the end tile. Just a little smiley face because we're really happy. Okay, but in case we haven't found the end tile, we want to start checking other tiles. So the first thing that we're going to do, and that's really crucial, we want to move the current tile and move it to the closed list, and we want to remove it from the open list. We remove it, open list dot remove, and then say the current tile, and then we say closed list dot add, and again current tile. Okay, perfect. Now we're going to check what are the adjacent nodes of the current tile, and we're going to store all these adjacent tiles in another list. We're going to make a new list, again of the vector2, vec2, and we're going to call this adjacent tiles, and we're going to make a method here, and we're going to call that method get adjacent tiles. And we're gonna make this really nice, this adjacent tile, because this method, because later on we want to check every adjacent tile, whether it's walkable, whether it's in the open list or in the closed list, and all we have to do is place a loop around this adjacent tiles list, and we can repeat these search algorithms. So we're calling this method here, but of course we also need to make this method. So I'm gonna say public void. Oh, of course, not a void. That would be ridiculous. No, I want to have a list of vector2. Great. I'm gonna say get adjacent tiles, and of course the current tile that we pass along is a vector2. Okay. So the things we're going to do inside here, we're going to check if it's, well, the adjacent tiles, whether these adjacent tiles are inside the boundary of our grid, and if they are actually walkable. First off, I have this vector2 list, which is the list that we're going to return at the end of this method. I'm going to say tvec2, and we're going to call these the adjacent tiles is new list. Perfect, just like that. And we're also going to keep track of a current adjacent tile that we're working with, that we're checking things with. Adjacent tile. Okay. The first thing that we want to do is check the tile above us. We're going to say adjacent tile is new vector2, and we're going to say current tile dot x, which remains the same, but the current tile dot y, well, that's going up one step. Perfect. Then we do a little check. Why is that wrong? Current tile, oh, of course, dot y. Okay, if adjacent tile dot y, that's what we're going to do, adjacent tile dot y, if that is lower than the actual Astar test grid height, that's important, because let's say we're at the top of our grid. Just pick our, let's say we're here at coordinate 0, 1, and we're checking above. Well, that value doesn't exist, so we're checking on that. So we're going to say grid height. If it's lower than the grid height, let me see, yes, and also whether the, I'm just going to copy this because it's a lot of typing. What I'm doing, I'm going to say at this position on the grid, so adjacent tile X and adjacent tile Y, if that is actually walkable, because if it's not, well, what's the point of checking there? Why should we add it to the list? But if it is walkable, then we want to add this to this adjacent tiles list. Add, and then just adjacent tile. Perfect. Correct? Yes. Now all we have to do here is copy this 3 times, and then we need to start checking underneath. Replacing the wrong word. Checking underneath. Tile to the right, and the tile to the left. Of course, we need to change the code here. Okay, let's continue. Underneath, of course, that means that we, instead of +1, we're gonna say -1. And instead of checking for the height, we just want to say it has to be larger or equal to 0. We can remove this entire part. Okay. And then all we have to do is add it to the adjacent tiles, which we already have. Then we're going to say check to the right. And meaning to the right means +1. We can remove the part +1 at the Y. Let's see, this time we have to check whether it's smaller than the width instead of the height. Perfect. And when we go to the left, we do -1. And just like underneath, here we have to say if it's larger or equal than 0. Okay, great. Optionally, we can add diagonal checking. But for this tutorial we're not going to do that. It's pretty easy. The only thing you have to do is say for -1 and -1y, and do the exact same thing for top left, top right, bottom left, bottom right, and so on. But just in case you want to do that, I've added this extra line because you can add that here. Okay, the last thing we need to do for this method to work is just return the entire list of adjacent tiles. Okay, perfect. We can minimize this, and we're going back to our Astar code. And let's have a look at the entire list. And what do we see here? We've covered all these points. We moved our current tile to the closed list, and we're now going to check each adjacent node, and that's what we're going to do. We got all the adjacent tiles. Get all the adjacent tiles. And then we're going to do a simple for each loop. For each vector 2, we're going to say adjacent tile in adjacent tiles. Perfect. The first thing that we want to do, the adjacent tile, Control Shift, the adjacent tile is not allowed inside the open or closed list. So for each adjacent, if it lies within the field, if it's an obstacle, or if it's in the open or closed list. Now we've already checked whether it's an obstacle, so we can skip that. We already checked it in the get adjacent tiles, so that's pretty awesome. We can already start looking whether it's inside the open list. Adjacent tile cannot be in the open list if not closed list dot open list, of course. Just have to really do what I'm saying right here. Contains the adjacent tile. If it doesn't, only then we can continue looking further. Then we have to say inside the closed list. Now, of course, I could add this closed list line inside the if statement here as well, but because it's a pretty long line, I want to keep things clear a little bit, and that's why I'm going to add it here. So if it's not in the open list and also not in the closed list, okay, then we're going further, and then it means it's available, and then we can start calculating the costs, the new costs, and that's this particular line. I'm going to copy and paste it right here. Okay, that's what we're going to do. I'm going to say the first thing that we need to do is open list dot add the adjacent tile, because it's a new tile that we've just discovered and it's available, and we haven't added it yet to the open list and the closed list. So now we can start adding it to the open list because it's an available option. Then we're going to make a temporary tile just so that we can spare ourselves the typing. I'm just going to copy the grid, and I'm just going to say here adjacent tile.x and adjacent tile.y, because I want to request the tile that is on that particular index. And then I'm going to calculate the cost. And we calculate the cost by saying the tile.cost is the cost of the previous tile, or actually better said the current, because we haven't changed the current tile. I'm gonna copy this line here, paste it, and instead of adjacent, we're still at the first tile that's being checked, so the current tile dot cost, and we have a step count of 1. Of course, we can use any kind of value here, for instance a step count of 10, and when you go diagonal you have a step count of 14, but in our case we're just going to keep it simple and we're going to say 1. Now we could say here our tile.total is the cost, tile.cost, and once we've done that, I'm just going to say add calculate the total amount. Now, of course the total is the exact same as the cost at the moment, but I just want to show you what we have so far. The only thing I want to do here is make this tile green, because it's a tile we've been checking. le.entityColor, and I'm going to say which one do I want? Of course I want the current tile that we have right now, the tile dot, and I want to get its cube because that's the mesh, and I'm going to say tile dot, what should we use? Green. I think green's pretty nice for this. And let's see what happens. Let me see. We get 2 errors. This needs to be capital Y, and we need to do some typecasting here as well. I think I forgot that on a couple of places. Yes, the exact. It's funny that I do the exact same error on so many places. Okay, integer here, integer typecast there. We try it again. Exciting. Of course, I haven't called the actual pathfinding yet, so let's just seek out some points. Let's start at 0, 0, and let's just go all the way to here, which is, you know what, let's just go all the way to there, to 99, and then saying 99. Okay, so we go to Astar test, back to our main file, make a new Pathfinder. I'm going to say Pathfinder. Path1 is new Pathfinder, and then we're going to say Path1 Need to pass along the grid. Mustn't forget that. Path1 dot search path, and then we're gonna say new t vector 2. We're gonna start at 0, 0, and then we wanna go to, we wanna go really far. What was it? 99, I believe, and 98. Now, if one of these tiles is not available, if it's non-walkable, then we're going to get this error. It is also possible that we have defined an end tile which is inside a, well, it's in a closed loop, which means that it could be surrounded by non-walkable objects. Now that's something we can adjust later, or perhaps I'll just leave that out of this tutorial, and that's something for another tutorial or something for yourself to find out. Okay, so our program closes immediately. That's not something we want. Okay, I've been looking for the error, what the problem was here, and you need to go to Pathfinder and go to the get adjacent tiles method, and I forgot to change the right and left checking. Of course I need to check on the x-axis, not on the y. That was the error, and that's why it was crashing. Also remove the accolades, because we only have one line after the if statement, and that means we do not need these accolades, and our code is being minimized that way. Okay, what I wanted to show you is that the algorithm we have at the moment is actually the algorithm that we started out with in the PowerPoint presentation, which is the Dijkstra algorithm. Yes, that's true. We actually have that working right now. And the only thing I want to show you here is that when the while loop is complete, now you know what, if the if, say even if the if statement skips, or yes or no, then we want to paint the start and end tiles red. Paint the start and end tile red. So we're going to say le.paint entity. I want to say grid. Of course, we need to do this again. The typecasting. We say startile.x and startile.y dot mesh. Dot, not a comma. Dot cube. And we want to say tile dot red. Forgot one typecast here. And of course we want to do the same thing for the end tile, and apparently I'm forgetting something else as well. What's the problem? Oh, I shouldn't use paint entity. I mean color entity, or what is it again? Color entity color. That's the one. Okay, and let's just see. I've set the path to, where did I set it? Here. I set the path to 2020, and just, well, let's just see what happens. Oh. Again. Guess I keep doing that for the rest of the tutorial. Found the path, and ooh, that looks good. Well, believe it or not, but we have the Dijkstra algorithm already working, and as you can see, a lot of the green tiles are being used, even though a lot of them are not per se necessary, and you will see later on that the Astar algorithm is going to solve a lot of problems. The only thing that Astar adds to the Dijkstra algorithm, because that's basically what it does, it adds a little thing, is called the heuristic, or better said, or otherwise said, a sort of guess for our algorithm to calculate the shortest path. And this so-called guess is always called a heuristic. And there are different heuristics for Astar, and a common used heuristic is called the Manhattan heuristic, and that's also the one that we're going to use in this example, because it's really a good working heuristic. But for example, for a terrain, the Manhattan distance would not be ideal. But first off, I'm going to show you the Manhattan distance heuristic. I'm going to go back to my PowerPoint. Here's the Manhattan distance. Okay, so the Manhattan distance is this extra value that we add to our total cost. And Manhattan, of course, this is based on Manhattan in New York. And if you, well, I think you have ever seen that you have seen an image of New York or a movie with New York in it, and then you can see that Manhattan is built up out of these straight going streets and all these straight cross sections, no curves in them. And if you want to go from block A to block B, you can go there in this straight line. But if you want to say go for instance to this point here, then you always have to, you can't go down, you have to go into a first horizontal, then vertical, or first vertical, then horizontal. You can't go diagonally. You can't. So the Manhattan distance, for instance, from A to B is 1, 2, 3, 4. And that's why this value here is 40. So we have a base cost of 10 for every step. Then we have a Manhattan distance. Of course, this can differ. This Manhattan distance is mostly based on the amounts of step you take from the tile you're checking with. So in this case, the adjacent tile. So we're not actually checking from the current tile we're on, but the adjacent tile. And the adjacent tile is 1, 2, 3. So that means 30. I said 40 just a moment ago, but I meant 30. And these two together, this is the cost, this is the heuristic, and together that is 40. And that is what the heuristic is in Astar. So pretty much the entire Dijkstra algorithm, but by simply adding this extra guess value, we turn the Dijkstra algorithm into an Astar algorithm. Okay, and let's implement that. We're going to say here, calculate the Manhattan distance. So we're going to say tile.heuristic is Manhattan distance from our adjacent tile. Now, of course, the Manhattan function or method doesn't exist yet, so we're going to make that. I'm going to say calculate the Manhattan distance. Just type that. Adjacent tile. The adjacent tile is a vector 2. Vector 2. I'm going to make it a public. Of course, it needs to return a value, and that is an integer. And how do we calculate this Manhattan distance? You're probably wondering that. Well, we're going to make a simple integer. We're going to call it Manhattan. Very convenient, right? Convenient. And what do we want to do next? We want to subtract the end tile. We probably have to typecast that. We want to subtract the end tile dot x minus the adjacent dot x plus the same thing for the y values. And that means, for instance, we're on adjacent tile 3, 3. Let's say 3, 3, and we want to get to 4, 4. Now that means that we have to get the end tile x, which is 4, minus the adjacent tile x, which is 3. So 4 minus 3 is 1, plus the end tile y minus the adjacent tile y, which is also 1. So that means 1 plus 1 is 2. So from going from 3, 3 to coordinate 4, 4, we have a Manhattan distance of 2. Now, of course, it's possible that these numbers are reversed. For instance, we could also go from 4, 4 to 3, 3. Just in case in our calculation something goes wrong, just in case, we're going to add something extra, which is called an absolute value, which means that even if our our subtraction sum is a minus value, we want to get the positive value out of that. And we can easily do that by calling the math class and using the apps function. And we do the same thing for the y. Okay, and then of course we have to return this value, return Manhattan, and then this function is complete. And as you can see here, calculate the total amount. We're going back to the actual calculation here, is the cost plus the tile heuristic. And now we have the Astar algorithm complete. So when we look back at this list here, this is actually entirely Dijkstra, but this word here, calculate, that's all the difference there is into Dijkstra and Astar, because the calculation only adds the heuristic value. Let's just see what happens. And now we can see something totally different. Instead of getting this entire field turned into green blobs, we now have this really nice looking, well, paths of tiles that are being checked. Of course, this is not the exact path that we're going to walk as a character, but at least we have narrowed down the amount of tiles that we're going to check. And this is awesome. I mean, you have to admit, this is really cool. And to, well, let's just extend this test a little bit with some extra values. You know, I don't want to go this way, I want to go all the way to there. Yes. Okay, they're working. Okay, well, that's pretty interesting. It first starts off with this really big blob here, meaning that all these values are very close to each other, but then in this part you can see this very thin line, which means that only this line has very close together lying values, and then in the end it starts to get a little thicker and then thinner again, and that's really cool part of Astar. And you can see that these areas here, they are being left out there. Well, their values are way too high. Okay, cool. Just to test this even further, let's add another Pathfinder. I'm gonna make a second one. Number 2. Path number 2, and we're gonna start this one at coordinate 80, and we'll wanna go to, I don't know, 60 and then 12. Hopefully he finds it. Yes, he found one. And let's see how that one looks. Okay, now of course these tiles are also green, so they might overlap. But you can see this tile also finds its exact path on the grid. And, well, it looks really nice as well. Okay. So, what are we going to do next? We're not done yet. No, we're at one of the final stages of our PowerPoint here. Getting the actual path, that's where we are. We're near the end. And let's be honest, this tutorial is pretty long, so that might be a good thing. Okay, let's continue with our Astar showcase demo, and one of the last things that we're going to do is we need to actually calculate the actual path that we're going to take. I mean, we found the end tile, but we haven't found the actual path that a player should be taking. And we're going to visualize that by using spheres, and we're going to place them on top of those cubes. So I'm going to the tile class, I'm going to make a ball or sphere, whatever you want to call it, I'm going to give an extra parameter to this tile constructor. Again, it's a T-mesh, but this time a ball. Oh, a ball, not a bool. Oh, forgot the comma. Loop. Also want to copy this line. Okay. We want to say ball. Copy the entity called ball. We do not actually want to show it. We do want to position it and scale it a little. For position, we're gonna say new position, new tvec3, and we're gonna say position.x. I'm just gonna copy this. Okay, the z value remains the same, but the y value, we need to add something. I'm just gonna guess for 1. I guess that's okay. The scale, well, I guess we want to a lower scale than an actual size of a cube, because that will look really bad, I think. I don't know, dividing by 2 might be good. And of course the scale, not the position. That would give a really strange effect. Scale entity, and we want the ball to scale, not the actual cube. Okay. Okay, so we need to go to the Astar tests, and we have to add that we have to add this ball mesh, otherwise the code won't work. And of course we also have to make this ball. I'm gonna do that right underneath the cube that we create as a prefab LA create sphere. Oh, not spotlight, sphere. And we're just gonna give it 8 spheres, that's enough, I guess. Sphere. Little typo, yes. Do we want to hide this ball? Yes, in the beginning we want to hide it. Only when we find the actual path we want to make it visible again. Okay, we're gonna go back to the Pathfinder class, and right at the end of the search path function we're going to show the path. Show the path, yeah, I think that's a good name. Show path. Path or path. We're gonna say public void show path. Okay. What do we want to do? First off, we need to keep track of whether we have found our start position. If you're wondering why we're checking our start position, that is because we are checking our path from our end tile, and we do not start from our start tile. So we start checking from our end tile, and once we found the start tile, we stop checking and our path is completed. So in the beginning, of course we haven't found our start tile yet, otherwise there is nothing to show. We want to keep track on which tile we currently are. Current tile, which is in the first case, of course, the end tile. And we want to keep track of what the actual path is, and we do that with a vector2 again, and then we're going to call this path tiles. Is new. Ah, there we go. Okay, we're going to open a while loop while the start has not been found yet. As long as that's false, we want to say well, first we want to get the adjacent tiles from every current tile. Now let me rephrase that. We want to get all the adjacent tiles from the current tile. So we're going to store that again in a list. I'm going to copy this line, and I'm going to call it adjacent tiles. And the cool thing here is that we can call the method that we've created before get adjacent tiles. So that's pretty cool. That's really good programming right there. Okay, and then yeah, well, we want to what do we want to do? We want to check to see what the newest current tile is. And how do we do that? We're going to check whether one of these tiles that we're going to check, whether one of these adjacent tiles is in the closed list and in the open list. That is a requirement. And if that's so, we also want to check whether the cost of this adjacent tile is lower or equal lower or equal than the grid with the current tile on the grid, which we are checking. Okay, so let's just start typing that. First off, we want to check if it is the star tile. Oh, need to go into the for each loop first. For each vector 2, the adjacent tile in adjacent tiles. Forgot an S here. Please add that because it makes it a lot more logical. Then we want to check if it's the star tile. Check. Of course, if it is the star tile, then we do not need to look any further, and we've already found that the path is closed. Once again, I'm doing this with a little bit more type work than actually necessary, but I prefer this myself instead of just typing the entire vector. Just the vector. I like to type the entire vector here. Okay. Oh, start tile.y. Okay. And what I want to say here, well then, if that's actually true, then I want to say start found is true, because we found the start tile. That's the tile we're working towards to. And if that's not the case, well then we are going to go into another if. It cannot be, it has to be inside the closed as well as it has to be inside the closed as well as inside the open list. Press the wrong button there. As well as in the open list. Okay, how do we do that? We've seen that before. Closed list contains, and there it is, adjacent tile. Or open list contains adjacent tile. Okay, now if that is actually the case, if one of those adjacent tiles is inside the closed list or in the open list. Okay, let's continue with this. The only thing left to do here is we need to check whether the cost of the adjacent tile is lower or equal than the cost of the current tile we are at. So we're going to say if grid, and then we'll need to specify the index, which is the adjacent tile. And we have to do this very long typing here, which is adjacent tile.x. And then we typecast it to the integers adjacent tile.y. And then we can say finally cost. Whew. And then we have to say if it's lower or equal to the grid, but instead of the adjacent tile we say current tile. And if we think about that for a second, that makes perfect sense, because the cost towards the closer you are at the end tile, the lower the cost, or sorry, the the lower the actual cost is. Because to get to that particular place, to get to the actual end tile, you have a very high cost, but the tile before the end tile has a little lower cost, or it might have the same cost. Sometimes it depends a little bit on how paths connect to each other. And just in case things don't work out correctly, we should also check whether the cost of the adjacent tile is not 0, or is higher than 0. That's even better. It's just a precaution, because it's probably not even necessary, but just in case is always better. Okay, so the only thing left to do in this particular code block is we need to change the current tile, because we have found a better tile. So we can say current tile is the adjacent tile. We also mustn't forget to add this new adjacent tile, add this adjacent tile to the path list. So path tiles.add, and we're going to add this adjacent tile, and this way we can build up our path tiles one by one. And I want to do something else here. I want to show our entity and show the ball we just added to our tile class. Show the ball. le.show entity, and then we have to say adjacent, this one, dot ball. Okay, so we're going to show it. Do I also give it a color? Have I already done that? I haven't done that yet, so I'm just going to do that right here in the tile class. Every single ball just gets the color yellow. Doesn't exist yet, so we're going to make that. Okay, yellow is 255 because red and green together. Is that correct? Red, green. Well, I don't know. Well, anyway, that's yellow. It's late, so it's a good excuse, right? Okay, let's test it. Exciting, exciting, exciting. I did something wrong there. That's not exactly what I want, but I forgot to say ball here. That's of course really important. And we also need to check if this code is actually right. I just type now. Okay, so we have a path, but it's not entirely correct. We have a jigsaw pattern here, but still we're getting close, but it's not entirely correct yet. Although it looks kind of cool this way, but still we haven't found the correct path yet. The way it's going now is we have this ball, then we check this one, then it goes to this one, then it goes to this one, then to that one, then to that, and although that is exactly what should be going on, it's not what we want. The code is actually doing exactly as we tell it to, but we need to prevent this double trace, double path here. We need to do something about that. But still, the result looks pretty cool. Okay, so let's go out and let's see what we can do about that. Okay, I think I found the problem here. As soon as we have found an adjacent tile which has a lower cost, then that means that we're actually done searching. So we do show the ball, but if we are continuing in this loop and we find another shorter path, then we're gonna a shorter cost, then it's gonna add that ball as well. So we don't need to do that. So that means all I have to do here is break it, and if I do that, the problem should no longer exist. And there we go. Isn't this great? I mean, look at that. We have a starting value here, starting tile, and then we go whoop, whoop, dip, dip, all these yellow lovely spheres here, and we have a nice path that we follow right onto, oh, here we have intersecting spheres from the other path that we're searching from, and all the way to our end tile, and this is our actual path. Of course, when you work with a player, you can, instead of just using a void, you could actually return the path to the player so that the player can start walking from node to node. But we're not going to do that in this tutorial. I think this tutorial covers enough ground for one tutorial. And that means we're towards the end of this tutorial. Oh no, we have one thing left, and that is the improvements. I'm not gonna do much coding here. I'm just gonna show you some improvements that can be added. And the first one, and the most important one here, is instead of the Manhattan, where is it? Here it is. Instead of using Manhattan, you can use different kinds of heuristics. For instance, for this kind of grid, Manhattan is quite ideal. It works really good. But when you work with a terrain, it's not that good. For instance, if we have a very large mountain and we can cross this mountain, we do not worry about slope angles and stuff, but if we have to cross this mountain, then troops or a player can be very slow moving up this mountain, and going directly over this mountain while taking a small route right to the mountain is a lot faster. And well, that's something the Manhattan distance doesn't take into account, so you need to find out some sort of different heuristic. But that is something for a different tutorial, or something that you just have to find out for yourself. Another thing that's really cool to look at is when looking at the get adjacent tiles. I already mentioned that you can use diagonal searching, which works really well. In this case, you just have to add a couple of lines. And one other thing you have to what you have to keep in mind is that every time we start searching for adjacent tiles, and let's say we find all four directions, above, underneath, right, left, it will always start checking above, and then underneath, then right, then left. So if our object is to the left, then we still have to check above, underneath, and the tile to the right first. So you could try to think of a mechanism that adds some sort of Manhattan to the adjacent tile searching as well, so that it seeks, the tile I am going to search towards is to the left and to the top and above me. So that means I'm going to look for above first and then to the left, and only if then is nothing found, then also check these. So, you know what, we're just going to change that for now, because that will give you completely different results. While the actual path is still the shortest, and it's actually the same path with costs and heuristic, the actual path will be different. You see that? And wow, that's a really big difference. I didn't expect that. But still, is it the shortest path? It is. It's still the shortest path, but you can see by just switching two of these lines we can get a massive amount of change here. I'm really surprised that the amount is so large. Let's just swoop another line. Now to the left is always the last one, because we're not going to the left, we're always going to the right, and then above, and then underneath. So I'm going to do that. This one should be really cool. This one should be really also not really fast. Wow, that really amazes me. It's also really slow, actually. Did not expect that as well. So the lines we had at first were actually the best. Who would have thought? So first to the right, then no, that was not the first one we had. So, like that. One last test. Yeah, this one was actually the fastest. This way you can see how crazy it goes with Astar pathfinding by just switching a couple of lines. Okay, let I just close this off. So I'm gonna close C# here, Visual Studio. One last thing that I want to talk to you about, the PowerPoint, the starting project, which means the camera flying around, and the C# project are in a zip, and of course the final, as I close it here right now. These are going to be added to a zip file, and they can be downloaded from the Leadwerks website. I really hope you enjoyed this tutorial. If you have any comments or questions, please ask them in the forum. One last thing I want to say is, I know there are a lot of things in this tutorial that are not entirely correct, or there might have been better ways, but it was just a way to show you how to create the Astar algorithm in C# using the Leadwerks engine. I hope to see you again at a next tutorial, and happy coding. Goodbye.